7 p.m. Well, I'm on Friday. Just a bit of research and I'm not going to leave right up front. I'm just going to go on Saturday morning. Just be home. I'm not complaining.
So what I'll start off with on Tuesday is the actual structures of the things that do this, and I think that's what we're talking about because it'll make the model make a little more sense. I think to actually see how you can do that with a polypeptide. But before doing that, I want to make a final kind of justification for the importance of the structure of this kind of channel. And it has to do with the nature of the overall layout, the logic, the engineering logic behind electrical communication. So what I haven't talked about at all is how you get that action potential in the first place, and that actually will come kind of at the end of the discussion. But we'll get there, but let's just say it has been formed. So it moves along the axon body, so it gets to the axon terminus, and ultimately triggers the release of neurotransmitters. That's the job of this particular action potential right here, this presynaptic cell. And it so happens that the way that works is that the movements of sodium and potassium that are the action potential, the selective changes in permeability going along from left to right here, when the action potential arrives at the axon terminus, that gets converted into changes in permeability for calcium. So it completely changes its essence at the axon terminus. And ultimately, the entire purpose of all of that intricate action potential business is to send a signal to the axon terminus to bring in a bunch of calcium, to have a spike in calcium concentration in the presynaptic cell at the very, very tip of the axon. And that ultimately says release neurotransmitter. The good news is the change in calcium permeability is performed by voltage-gated calcium channels that look exactly like voltage-gated sodium channels, which look exactly like voltage-gated potassium channels structurally. So we can do one structure description, 10 minutes worth of structure of a voltage-gated channel, and know them all. The only thing you need to know is which ion they are specific for. But the mechanisms are entirely superimposable. That's the good thing. All right? So what has to be accomplished is the propagation of the action potential. That we're done. We'll talk a little bit about the structure of the things that do it, but there's no additional concepts there. How it gets converted into a calcium permeability change at the axon terminus, and what that accomplishes, which I can tell you real simply, is it causes neurotransmitter vesicles to fuse. So you already know, tethering, docking, fusion, the mechanics of that process, there's nothing new there. So once you have figured out the placement of voltage-gated channels and you have some sort of appreciation for what quote-unquote voltage gating means, then you're done with the presynaptic cell. That's the good thing. And the rest of it is just what does a neurotransmitter right here get us in terms of making this cell fire. And we'll do that last in the sequence. Okay? So what's going to happen next is a description of the structure, the very paradigmic, iconic structure of a voltage-gated X channel, sodium, potassium, calcium, they're all the same, and then the mechanics of voltage gating, what we can learn from the structure.